So you can see here we have a triangle set up where I've already put up the marked the centers that we've created that you're working on a GeoGebra assignment to create. Um, I haven't put all the different line segments. I've hidden those. They're all there if you really want to see them. You know, if I do that, you can see they're all there. But I've taken them out for now because I don't want to have to look at them. All I have are the circumcircle, the end circle, the end center, centroid, orthocenter, circumcenter, the midpoints of the sides. So, and then the Euler line right here, which when you are doing your GeoGebra assignment, you'll see that this orthocenter, centroid, and circumcenter are all on that Euler line. So what I'm going to do in GeoGebra here is I'm going to kind of show a couple theorems on why they're true, and then we'll switch over to a different presentation tool, and we'll prove them and justify why they're true, where I can write it out. Okay. So the first thing is this orthocenter, centroid, and circumcenter are all on the same line. Furthermore, you might notice as I move this around that there does seem to be kind of a ratio there, right? Like the centroid seems to be closer to the circumcenter than it is to the orthocenter. So we can do a little investigation here. Let's just measure the distance of the length. Let's measure the distance from the circumcenter to the centroid and from the centroid to the orthocenter. And lo and behold, as we do this, you can see the distance from the centroid to the orthocenter is twice that of the distance from the centroid to the circumcenter. And so this will always be true. There's a little bit of round off error here. So like right there, it looks like it's not quite twice, but that's just due to round off error because it's only rounding to one decimal place. So you can drag yours around. You'll see that that always holds true, that the centroid of a triangle trisects the segment joining the circumcenter and the orthocenter. So that's a theorem that we're going to investigate, kind of a cool result, that the centroid of a triangle trisects the segment joining the circumcenter and the orthocenter. So we're going to let this kind of live down here. So that's one result. That's kind of nice, kind of interesting, kind of unexpected. Here's another one. On this, I'm going to extend these sides out to where we can see their extensions, how far out they go. And I'm just going to put 3 random points on the, or sorry, not 3 random points, just a single random point on this circumcircle. Okay. Now, from this point on the circumcircle, now notice if I place it on that, I can drag it around and put it anywhere I want on the circumcircle. From that, I'm going to drop perpendiculars to each of the sides. And notice I'm choosing the extensions here so that even if we go outside the circle, these will work. Okay. Let's make these. I guess we'll make them. I've already used red, blue, purple, green. So, and orange is the line. And we'll make it, let's do orange here. And we'll just make them dashed. Now, this is not super important, but for us to spend our time on, other than it just makes things a little easier to look at. Okay. All right, so we can see this intersects the 3 sides. So I'm just going to put the points in here where they intersect. Here's this point. This intersects that side that is perpendicular. This is right here that's perpendicular. All of those are points where it intersects kind of the feet of the altitudes we dropped, so to speak. Now, what's interesting about these points is if I draw a line through two of them, check that out, it is automatically going through the third. Okay? So if I drop those perpendiculars from any point on the circumcircle, it turns out they're all collinear. And I can move this around, all right, the circle, and they're going to stay collinear. And this is going to be true for any triangle at all. Okay? Change the triangle. Notice these are still collinear. I can move the circle around. These will stay collinear. Okay? So, it's kind of an interesting result. This is called the Simson line, and we'll go ahead and write that up. Type it in here. That the three perpendiculars from a point on the circumcircle of a triangle to the sides of the triangle intersect the sides in three collinear points. The line is called the Simson line. Simson, no P, just S-I-M-S-O-N. So, we have these two results that we've just kind of seen here in GeoGebra. We kind of justified that they're true. So now we want to prove them and think about how do we know that they are always true. So we will do that in a different app in just a moment. So now that we've seen these theorems in action in GeoGebra, let's talk about how we prove them. So I'm going to try to draw some pictures here to help us with this. So let's say we have a triangle. Let me make it a little bit bigger. A, B, C. Okay? And what we're trying to do here is prove that the centroid trisects the segment joining the circumcenter and the orthocenter. Okay, so the centroid, remember, is we join all the, I'll do it in red. So the centroid, we join the midpoints, the medians like so. And so we can kind of guesstimate where it's going to be based on that. All right. So let's let the centroid be G. Be the centroid. Okay. And then we're going to let, we need the orthocenter, or let's start with the circumcenter first. So the circumcenter is the perpendicular bisectors. We'll do that in blue, so perpendicular bisector here. So looks like it's going to be about here. So I'll let that be O. Okay. O be the circumcenter. And then remember, the orthocenter comes from the altitudes to where we drop this like straight down here and get that, and then do the same over here. Okay, and let's call that H. Okay. All right. Now, my strategy is to consider this line right here. I want to prove that OG, we want to show the length of OG is half the length of HG. Okay. Now, my strategy to do that is going to be to look at these two triangles right here. Okay. So, notice that these two triangles share this angle, right? So they share that angle, and I'm going to convince us in just a second that they are similar by some arguments in just a second. If I can show they're similar with a ratio of 2 to 1, I'll be in business. Okay? So, in order to prove this, I'm going to take the circumcenter O, and remember that I can draw the circumcircle using that. It's not a very good circumcircle, but it will have to do. Okay. So I'm going to go from C out through O to a point out here, I, on the circle. Okay. And remember, this is a midpoint opposite A. We'll call it A prime. So my claim here is that since this is the center of the circle, this is congruent to this, right? And furthermore, A prime is the midpoint of CB, so this is congruent to this. Okay. So, in other words, CO equals half of CI, and CA prime equals half of CB. Okay. And they share this angle right here. So triangle CAO is similar to triangle CBI with ratio 1 to 2. Okay. So we have those right there. So this tells me that also IB is twice OA prime. Okay. So that's just looking at the third side over here. All right, so we have this ratio right here. Now, the next thing I need to do is make some claim. I'm really trying to relate this triangle to triangle AHG to A prime OG. So the next thing I want to do is look at this right here, this quadrilateral AIBH. Okay, AIBH. It's kind of a lot to say there. AIBH. Now my claim is that this must be a parallelogram. Okay, so claim is that AIBH is a parallelogram. Okay. Keep in mind what these are. A is a vertex of the triangle. H is the orthocenter, so it lies on an altitude from A down to here. B is a vertex of the triangle and lies on the circumcircle. I is a point on the circumcircle that is the extension from C through the centroid out to here. Okay. So why is that a parallelogram? That's a good question, and it's one I'm actually going to leave you to fill in the blank on, okay? There's a question in a problem set that's upcoming that asks you to fill in the details of this proof, and that's the detail I want you to think about a little bit more on your own, okay? Now, so if that's true, however, then AH is congruent to IB. Okay? So the distance from A to H must be twice the distance from O to A prime. So if we go back to these triangles here, we know OA prime is half this length AH. Okay? We know that they share this angle right here. So we have that angle HGA is congruent to angle OGA prime by vertical angles. Okay. Furthermore, since we know that this angle triangle CA prime O is similar to the larger triangle there, CBI. We knew that this A prime O must be parallel to BI. And since BI is in a parallelogram with AH, it must also be parallel to AH. So we have two parallel lines right here, and therefore alternate interior angles gives me that these angles match up. So angle HAG is congruent to angle HAG prime G by alternate interior angles, which is a Euclidean theorem that we have not proven, but I'm trusting that that's a familiar enough one that we're allowed to use it. So therefore, the triangles AHG and triangle A prime OG are similar, right? Because they have angle, two angles that match up, so the third angle is going to match up as well. And because of what we proved up here, that AH is twice OA prime, they're similar with a ratio of 2 to 1. And since they're similar with a ratio of 2 to 1, we look at the sides HG, and it must be twice OG, which is what we wanted to prove. Okay? Lovely. So now that we've proven this, we can move on and look at the Simson line theorem. Okay, so we have these three perpendiculars from a point on the circumcircle to the sides of the triangle. Okay, so we'll again start with a picture here. Let's say we have A, B, C like so. And I'm going to kind of extend them out, because we know that sometimes we need to look a little further out to get these. And there's some circumcircle around this. And I should be able to choose some point P on that, right? And then from P, I can create perpendiculars to each of the sides, like so. Okay. Let's call these points D, E, and F. I'm sorry I drew my picture so it ended up in my theorem there, but such is the way of life. So in order to prove this, we actually need kind of one lemma, one theorem that we haven't yet proven. And that has to do with cyclic quadrilaterals. Okay, so that's a quadrilateral that can be inscribed in a circle. So this is a common theorem in Euclidean geometry, and I'm just going to talk through it really quickly. A quadrilateral is inscribed in a circle if and only if the opposite angles are supplementary. Right. Now, the reason for this is if we have some circle, it's a really good circle, we have 4 points on it, so we have a quadrilateral here. Well, if we look at opposite angles, like look at this angle right here, it intercepts this arc right here. Now, if we compare that to the opposite angle, it intercepts this arc right here. So their intercepted arcs add up to 360 degrees. And since an angle is half the measure, an inscribed angle is half the measure of an intercepted arc, which you might remember from circle theorems in high school geometry, and if you're not sure on that, you can look this up. The measure of an inscribed angle in a circle is half that of the intercepted arc. These intercepted arcs add up to 360. Therefore, these two angles must add up to 180. Okay? Now, that's helpful here because if I look at points P, D, A, and E, P, D, A, and E. Well, notice that if I look at that quadrilateral, we have a right angle at E, and we also have a right angle at D. So those opposite angles are supplementary, and therefore the other two must also be supplementary. So they are cyclic. They lie on a circle. Okay? So I could figure out what that circle is. I'm not going to draw the circle in because it's going to get kind of ugly. Okay? But that we do have cyclic quadrilaterals. Okay, or not cyclic, yeah, cyclic quadrilateral there. All right, now similarly, I'm going to call that 1 because we're going to come back to that. Similarly, points P, A, C, and B are cyclic for the exact same reasons, right? P, A, C, and B. Okay? They're cyclic because, well, they're on a circle. we can see them there. They're all on the circumscribing circle. And then we can look at P, D, B, and F. So P, D, B, and F. Here again, we have right angle, right angle. Therefore, these must be cyclic. Okay? So that's point 3. Okay. Now, if I look at one of these, let's do P, A, C, and B. Let's do the second one because we already have the circle drawn in this case. Okay. If I look at angles P, A, C, and P, B, C. Okay. PAC, PBC. Because those intercept the same arc right here, those two angles are going to be congruent. They're inscribed in a circle and they intercept the same arc. Therefore, they are congruent with each other. That we're going to make that argument several times over. So if we start with the first one, which was P, D, A, and E, right? this right here. If we draw that circle in, we would get several congruent angles. We'd get angle PDE is congruent to angle PAE because they subtend the same arc in the circumscribing circle around this red quadrilateral, just like the argument I made with just a second ago. I would encourage you to pause and slow down and confirm this for yourself and draw yourself pictures, but this is it, the reasoning is exactly like I just showed you. Similarly, PAE must be congruent to PAC. From the second one, the one we drew on here, we have that angle PAC is congruent to angle PBC, PAC, PBC, that is what we just said a second ago, and also angle PBC is congruent to angle PBF. Okay. That's just from the fact that, you know, that's a different point on the same thing. Same thing with PAE and PAC, that's just extending the side. Okay. This comes from they subtend the same arc. This comes from, we're just renaming it essentially. This comes from subtend the same arc. Here we're essentially just renaming it with a different point on the same line. Okay. And then from the third one, we have that angle PBF, okay, is congruent to angle PDF. Okay, so here, remember, we have P, D, B, and F. P, D, B, F. We're looking at this cyclic quadrilateral right here. So we have PBF is congruent to PDF by the argument that they both subtend the same thing. Okay. Now notice I was very intentional about the way I wrote these to say PDE equals PAE, PAE equals PAC. So ultimately we're getting a ton of congruences here. PAC is congruent to PBC. It's congruent to PBF. PBF is congruent to PDF. Okay. So angle PDE, if we follow that chain, it's congruent to angle PDF. Okay, PDE is congruent to PDF. That tells me that E and F must lie on the same line. D, E, and F must lie on the same line. So D, E, and F are collinear. And remember, we call the line they lie on the Simson line. Okay. Now that we have that, I want to talk about one final theorem that is very useful in dealing with several different things. One that we didn't show in GeoGebra, but I just want to illustrate it here, and then I'm going to refer you to the proof, which is in your textbook. Okay. So if we have a triangle, like so, the claim here is that if I bisect any internal angle, okay, so let's say we have this A, B, C, and then it's going to intersect at D over here. The claim is that this internal angle bisector divides the opposite side into two segments that are proportional to the sides opposite the angle. Okay? So, or adjacent to the angle, I apologize. So what we're claiming here is that the ratio between AD and BD, so the ratio of here to here, must be the same as the ratio of AC to BC, the sides adjacent to the angle. Okay? So we have that right there. That's the idea. That's true for any three of, like if I look over here, let's call this E, it would also be true that BE over CE would be equal to AB over AC. Okay? And we can do it for the third side as well. The proof for this is theorem 4.5 on page 158 in your book. And the proof is fairly straightforward. So I'm going to refer you to read that in your textbook on page 158 and look that up, because I've spent plenty of time talking through proofs already on this, and I think you can read through and understand that one on your own. But this theorem is going to be useful to us down the road, and is another just fascinating thing about the way triangles are structured, that this is always true regardless of what triangle we're looking at, even if it's strange and goofy and obtuse. This theorem holds, as do all those others that we've just looked at.